Right, evening, Sunday evening here in Drumfield. Going through these questions. Got a snow day forecast for tomorrow. Fingers crossed because I'm meant to be in school. So let's see. So I've got these Aqua Ions questions. This is what I'm going to use, but this is going to be in my head. I don't need to look at it, but I'm going to show you how you could, use it in the exam, even though you can't take it into the exam. Alright, Aqua Ions. Consider the following reaction scheme. So we're dealing with copper turning into all of these colourful precipitates and solutions. Already, let's have a look. Deep blue solution, pale blue precipitate, a greeny blue or a blue-green precipitate. So you should be having an idea already. So we're dealing with copper, and I already know copper. You don't have to write this down, of course you don't. But the copper one reacts with that, doesn't react with that, reacts with that, reacts with that, and reacts with that. And I know what all of these are already. Okay, so reaction number one. Reaction number one that makes a pale blue precipitate on the way to a deep blue solution. Well, reaction number one, a reagent that you could use is ammonia, because this is ammonia and this is excess ammonia, but also you could use OH minus. But you do not get a mark right in OH minus, you have to write NaOH, KOH, or something like that. Alright, you're not allowed to just write OH minus. The copper containing species that is formed, the pale blue precipitate, Cu is copper hydroxide, CuOH2, H2O4, no charge on that. And the equation, Cu H2O6 times 2 plus 2OH minus makes Cu H2O6, no, what am I doing? Cu OH2, H2O4, and if you've used OH minuses, you're going to form two H2Os. But if you chose to do this with two NH3s, you will make two NH4 pluses. Suitable reagent formula and equation for the reaction. Right, reaction 2 is from the pale blue precipitate to the deep blue solution. So we can do that. Excess or excess. How do you spell excess? This looks a bit weird, though. Oh yeah, that's because I spelled it wrong. Excess ammonia. You don't need the excess, I suppose. It just has to be a reagent, but I think I'd write it in. The copper-containing species, Cu, is this one. CuNH3 4 times H2O twice, and they want you to go from CuOH2, H2O4, the pale blue. We're going to put 4 ammonias in, so that's 4 NH3s. You will make CuNH3 4 times H2O twice. You'll kick out 2 hydroxides and 2 H2Os. Seriously, I just did that the other day in lesson and I've remembered it. I'm not cheating here. There's nothing else around. There's no mark scheme out. Just shows you what you can do with learning it. Okay. I don't sit at home thinking about this all the time. I've done it a couple of times and it sticks in your head. Saying that, I just need to check I haven't made a mistake, and I have. 2 plus. Does it want state symbols? So just going back and checking, I'm just neatening it up, alright? Just neatening it up. Reaction 3. Reaction 3 to give a blue-green precipitate with copper. There's your blue-green, so you're making copper carbonate. So you can't just write carbonate. Think of a carbonate. Sodium carbonate will do. Calcium carbonate. Would that do? Solid carbonate? Yeah. Yeah, that'll work. Anyway, sodium carbonate. I tend, as a rule, go for sodiums or potassiums. They always dissolve. Copper containing species, CuCO3, CuCO3. That's the blue-green precipitate. Very simple, this one. So reaction 3 is from CuH2O6 times 2 plus. You're going to add, this pen's dead. Doesn't look dead, does it? So let's add loads of ink. and a little lease of life. So in all of these, you're allowed to write ionic equations, so please do. Alright, it just makes your life a lot easier. In other words, I'm not including the sodiums, and 6 H2Os are kicked out. Number 4, I wrote this. Look back in notes for what this might be. Reaction for a yellow-green solution. Well, solution means it's going to be charged. The copper-containing species is CuCl4 2 minus. Reagent you could use for that. HCl. I mean, I would probably say concentrated HCl, to be honest. Because just hydrochloric acid normally doesn't do it. Conc HCl, but equally sodium chloride. Anything that contains chloride ions. So sodium chloride would do it. Just salt, table salt would do it. Alright, so CuH2O 6 times 2 plus is just a ligand exchange reaction. 4Cl minus. So Cl minuses are large ligands, so you make CuCl4 2 minus plus 6H2O. Done. Piece of cake that, wasn't it, really? How many marks? 12 marks for just knowing that. Ooh, wouldn't it be nice if something like that came up in the exam? Well, whatever exam you end up doing. I'll be setting it probably. I don't know, AQA might set one. Whatever, it'd be nice if one of them came up in the exam. This question is about test tube reactions of some ions in aqueous solution. This topic is called Aqua Ions. Alright, so included in this, by the way, it's often thrown in with your chloride, bromide and iodide tests with silver nitrate. They might also decide to do some like sulfate ion tests with barium from earlier in the course. Anyway, just be aware of that. They often throw these things in with other ions tests. For each reaction in parts A to D, I've cut out A. State the colour of the original solution. State what you have observed when it's been added. In each case, write an equation. Right, sodium hydroxide. So we've got iron 3 plus sodium hydroxide. The original solution is yellow. Observation after adding hydroxide is a brown precipitate. This is where we are. Okay, hydroxide, we're adding it, we're making this. Okay. It is there, quite close by, but I'm not looking at it. Just to show you, FeOH3, iron hydroxide, iron 3 hydroxide, and then 3 extra water ligands thrown in. Didn't ask for that, come on Norton. Brown precipitate, observation, forms, yeah that's fine. Equation, FeH2O 6 times 3 plus, 3 OH minuses, 3 plus, 3 OH minuses makes iron hydroxide, FeOH3, still 3 other water ligands on there, and therefore you have kicked out, you have formed 3 H2Os. Easy peasy. Does it want state symbols? No, but I suppose you could go aqueous. In an exam I'd encourage you just to put them in anyway. An excess of ammonia solution is added to copper. Alright, colour of original solution is blue. Observation, after an excess of ammonia is added, deep blue solution. Deep blue solution. You have to say solution, otherwise you do not get the mark. Equation. Right, well, a deep blue solution is CuNH3 4 times, H2O twice. You're starting off with CuOH2O 6 2 plus. You're going to add 4 NH3s. So in this case, we're going from the original solution here to here. So we've not done this one before. So 4 ammonia's in, 4 water's out. So this is 2 plus, keep forgetting that. And 4 H2Os. I feel like I need to just slow down and check that. 4 ammonia's in, 4 ammonia's in, 4 water's kicked out. Yeah. Sodium carbonate is added to aluminium. Alright, so the carbonate ones with aluminium, if you remember, aluminium 3 plus, these are going to fizz and they're going to give the hydroxide precipitate. Colour of the original solution, colourless. Observation, white precipitate, fizz, white precipitate and fizz, or effervesce, or whatever you want to say, bubbles given off. That's all you need to know, really. White precipitate forms and it fizzes. Equation is the one where you have to take a bit of time balancing. You just have to practice it. We're going to add carbonate, CO3 2-. We know that you're going to make aluminium OH3, aluminium hydroxide, H2O3. You know that you're going to make carbon dioxide, and you know that you're going to make waters, and hopefully you've practiced it. We do this by balancing the charges on the left hand side, 3 + 2-. We need to make this neutral. 3 of them, 2 of them, 2 aluminiums, 2 aluminiums, 3 carbon dioxides, 3 of them, and it's 3 waters. Next, page 3 of 15. Sunday night, what am I doing? Hopefully buy myself a bit of time tomorrow when I've got to take the kids to school. When anhydrous aluminium chloride reacts with water, solution Y is formed. So aluminium chloride is AlCl3. Anhydrous just means with no water, so white powder reacts with water, solution Y is formed. Well, solution, when you add an aluminium salt to water, you're going to make hexa aqua aluminium. AlCl3, 6 H2Os will go in, you'll make Al, H2O 6 times 3 plus, and 3 Cl minuses, is that it? And chloride ions. Yeah, complex aluminium Z. Cool. Given equations to show how the complex ion Z that can act as a Bronsted-Lowry acid. Alright, well we did this. You need to show 6 water ligands, 3 plus. We need to just show an H plus dropping off one of them. That'll be 2 plus, and that'll be an H plus. Do we need to check the mark scheme? Yeah, I'll just check the mark scheme. Smashed it. Right, or you can, or what it said here is you can have an H2O on here and have this as H3O plus. Both of them are acceptable, even though it's not written in the mark scheme, both of them are absolutely acceptable. The one that I did and the one I've just changed it to. Observations you would make when an excess of sodium carbonate is added to Y. Which one's Y again? Who's Y? Solution Y. Oh, the hexa aqua ion. So this is aluminium. I'll do the equation first. Hexa aqua aluminium, that's Y. Excess of sodium carbonate, well, whatever, the carbonate's not important, the excess bit is not important. You're going to make aluminium, OH3, H2O3, plus carbon dioxide, plus waters. I've just remembered how to balance it anyway. 3 of them, 2 of them, 2 of them, 3 of them. Observation 1, white precipitate. Observation 2, fizz. Aqueous potassium hydroxide. Okay, hydroxide ions, excess to solution Y. Alright, we're in interesting territory here. Because aluminium does something in excess hydroxide. Alright, 2 observations you would make, it's added until in excess. For each observation, given an equation for the reaction that occurs. So if you add hydroxide to aluminium, you're going to form this first, which is a white precipitate. So you're going to go colourless solution to white precipitate to colourless solution. Observation 1, white precipitate forms. Do I say, yeah, I'll say from a colourless solution. White precipitate forms is Al, OH3, H2O3, 3 H2Os, Al, H2O 6 times 3 plus 3 OH minuses. Solid, aqueous. Observation 2, the white precipitate dissolves and it forms a colourless solution. That to that. Equation 2 therefore, and this is one I reckon you'll be able to have any number of different variations of this. I'm just going to go and form this one because it's easiest to balance, I think. 3 more OH minuses come in, 3 H2Os are kicked out. solid, aqueous liquid. An excess of a given reagent is added to each of the following pairs of aqueous metal ions. For each metal ion, state the initial colour of the solution and the final observation, and write an overall equation for the formation of the final product. From the initial aqueous metal ion. Okay, so we're adding sodium carbonate to iron 2 plus and iron 3 plus. Alright, well the iron 2 plus will form FeCO3. Alright, and the iron 3 plus will form FeOH3 H2O3. I'm going to do the equations first. Why not? Alright, carbonate. Got a bit neater. 6 H2Os. Carbonate. CO2, H2O, just like the aluminium one. 2 of them, 3 of them, 2 of them, 3 of them, 3 of them. Alright, I've got myself 2 marks. As long as I check. Looks alright, looks alright, looks alright. Okay, initial colour. Yellow, solution. Final observation. Green, precipitate. Overall equation, done. Initial colour, iron 3, yellow. Je suis un fool. Pardon-moi. Iron 2 plus is green. Yellow solution is iron 3 plus. Brown. Precipitate. Don't get sloppy, Norton. Solid. Aqueous. Be neater than me. Alright, I'm doing this late at night on a Sunday. In an exam I would not write like this. I'm talking to certain individuals here. Maybe I should model neat writing, but I need to be quick. Excess of conc hydrochloric acid. Right, hydrochloric acid is just Cl- ions in this case. So it's added to separate aqueous... Oh right, this is an old question. I'm really sorry, but you're going to make COCl4 2-. It's an old question, my bad. You don't need to know the colour of the cobalt. We need to know QFeFeL. If that bothered you at home, I'm really sorry if you wasted some time looking that up. Anyway. Blue solution, yellow solution, otherwise known as yellow-green. Either of them are fine. You do need to know this one, but you don't need to know this one. In fact, I can't quite remember it. Cobalt H2O 6 times. 4 Cl- has come in. COCl4 2-. God, what colour are you? I think it might be pink. I think it might be pink. Let's have a look. I haven't looked at this for a few years. Pink. Ah, no, that one's pink. That one's blue. Don't need to know that. Just looking at it because I didn't know it. Used to be on the spec, not anymore. Quickly, amazing how quickly things drop from my mind if I don't need to know. An excess of dilute aqueous ammonia, NH3, is added to separate solutions containing aluminium and what's this? Silver. Silver with ammonia. Yes, you do need to know that, but it's not on our table. You need to know it from somewhere else. Anyway, aluminium H2O 6 times 3 plus 3 ammonias will form aluminium hydroxide, because that's what always forms with aluminium, apart from when you add excess hydroxide. And you'll have 3 NH4 pluses. Colorless solution, white precipitate, silver, Ag, H2O twice plus, silver, only 2 ligands, silver it's so shiny they all go in a liney. Remember that? That was when we used to have fun. That anyway, that's what it looks like. 2 ammonias are going to go in. And you're going to make this AgNH3 twice plus, and 2 H2Os are going to be kicked out. This is known as Tollens reagents. Colorless solution. Pretty sure of that. Let's have a look. Colorless solution to colorless solution. I hope. Yay, got it right. Because I'm pretty sure that Tollens doesn't have any colour. Silver in it. Silver and it's charged. Colourless solution. Oh, I was saying that it is a transition metal, so you might be thinking, why is it not coloured? It's not. Anyway, 20 minutes in. It's taking ages. I asked you a lot of questions tonight. A green solution X is thought to contain iron 2+. Alright, the presence of these ions can be confirmed by reacting separate samples of the solution X with aqueous ammonia and aqueous sodium carbonate. Alright, Fe H2O 6 times 2+ is going to be my ammonia one. Fe H2O 6 times 2+ is going to be my carbonate one. Alright, iron 2+ with ammonia. 2 ammonias will go in and you will get Fe OH2 H2O4 plus 2 NH4 plus. Describe what you would observe. Alright, 2 plus, I'll look this up a minute ago. Green solution, green precipitate, and then iron 2+. Okay, with carbonate, you make iron carbonate plus 6 H2Os. Aqueous ammonia, yeah. Green solution, green precipitate. They both make a green precipitate. Alright, cool. You get a green precipitate with both. Let's have a look. Yeah, done fizz. If you write fizz, you've lost the mark because you wrote fizz where you shouldn't have written fizz. Only 3+. Fizzes. Oh, calculation. Did I give you a calculation? Ugh. A 50 centimetre cube sample of solution X, right? We know the solution X contains iron 2+. Added to sulfuric acid, which is the H+, made up to 250. Alright, so you've got some Fe2+. Alright, I know it's FeH2O 6 times 2+, but it doesn't matter, because I know it's a titration question. We got 50 centimetres cubed of that. It was added to sulfuric acid, not interested about that, and it was made up to 250. The 50 centimetres of acid is just a red herring. It's all been made up to 250 anyway, so it's now 250. 25 of this sample. Alright, so there's going to be a factor of 10 in there. 25 of this sample was titrated with, take me to the burette, a 0.0205 mole per decimeter cube solution. Cubed? MnO4 minus cube solution of. Look, I just dropped it. I dropped the potassium straight away. Drop them like it's hot. At the end point of the reaction, the volume of. Okay, so you take me to the burette, and it's there, isn't it? Alright, state the colour change that occurs at the end point. So you're putting purple stuff into colourless stuff, or very pale green. Goes colourless, it goes pale pink, or permanent pink colour, or it ends up pink. It ends up pink. And give a reason. Alright. So you get this. Sometimes they call it a persistent pale pink colour. Because, how do you say that? MnO4 is in excess. Or you've run out of Fe2+, so the last drop of MnO4 minus won't lose its colour. That would work, wouldn't it? Write an equation for the reaction of iron 2 ions and manganate. MnO4 minus. I mean, I could show off here and just write it. But imagine you're in an exam and you can't. Because it's a 1:5 ratio. I remember that, you see. Some of you will. I'm writing the half equations. The Fe2+ turned into Fe3+. 4H2O, 8H plus, 5E minus. So you need 5 of these, 5 of these. So the overall equation is MnO4 minus plus 5 Fe2 plus 8 H pluses, which is why we need this the sulfuric acid, makes Mn2 plus 4H2O plus 5 Fe3 plus. You should be practiced at that because we did a whole thing on titrations. Alright, here's 1 mark. Use this equation and the 1:5 ratio to give. Alright then. So I'm going to start here. Start at the burette. Calculator. I can see it. It's on the top shelf. Right. Burette says 0.0205 times 18.7 equals divided by 1000 equals. There's moles of manganate. So I'll write that down here. I'm going to do that again. I don't feel like I wrote it right. 0.0205 times 18.7 divided by 1000. Let's do it again. 0.0205 times 18.7 equals divided by 100. 3.8335 times 10 to the minus 4. Moles of MnO4 minus. It took me a second to write that. Do that in an exam. Don't just write a number and leave it hanging there for the examiner to work out. They'll get annoyed with you. Alright, there's that many moles of manganate. So then you go to what's in the conical flask. If there's that many moles of manganate, you times it by 5. On my calculator, times 5. 1.91675 times 10 to the minus 3. Look, moles of Fe2 plus. Took me a second, just do it. In 25 centimeters cubed. Now I'm going back here. Times by 10, times by 10, times by 10. I'm laying it out nice, you see. I know it's all over the place, but it's clear. There's 0.011675 moles of Fe2 plus in 250 centimeters cubed. Alright, so what do they want? Concentration. Right, so I've got moles, and I've got a volume. Alright, so I know that moles equals C times V over 1000. I've got moles, you see. So, moles times 1000 divided by V. Moles times 1000 divided by V equals C. So that's 0.019675, which is still sat on my calculator up here, times 1000 divided by 50 is my answer. Don't press clear. Times 1000 equals divided by 50 equals 0.38335 moles per decimeter cubed. Please be right. So that's for sig figs. It doesn't. But do I do it to 2? No, I don't need that. I don't use this 50, you see. I'm gonna make it to 2 sig figs because that's not included in the calc. 3 sig figs, 0.383 moles per decimeter cube. You know, apart from like daft mistake, like numerical mistakes, writing down the wrong number, I've not made a mistake on one of them since, well, more or less, since I've started using that drawing the diagram thing about 7 years ago. It really helps. Okay. Coordinate bond is formed. Lone pair on the ligand is donated to the central metal ion. What's it say there? An electron pair on the ligand. You say lone pair, please. Lone pair on the ligand. Describe what you would observe when dilute aqueous ammonia is added dropwise to excess for copper. Alright, copper with ammonia you've got to watch out for. So what you're going to get firstly is you're going to get copper will form the hydroxide And then the hydroxide will form 3, 4 times H2O twice 2 plus that. Okay, ammonia, 2 NH3s, 2 NH4 plus, 4 NH3s, 2 OH minuses, 2 H2Os. See, I've done it so many times, I'm just do it. Put that plus there. State symbols, AQ, solid, solid, AQ. I'm just checking for mistakes again. Bear with me, I'm getting too tired to bother checking. Describe what you would observe. Blue solution. Blue precipitate. And the blue precipitate, deep blue solution. I want it to end now. I want to go to bed. No, I don't want a cup of tea and a chocolate bar. That'd be nice, wouldn't it? When the complex ion that acts as 1,2-diaminoether, you know, we haven't seen you for a while, mate. Our old friend, the Biodentate Ligand. The ammonia molecules, but not the water molecules, are replaced. That's interesting. Write an equation for this reaction. Okay. Well, let's start off with, we'll keep the water molecules in. If 4 ammonias are replaced by bidentate ligands, you're going to have 2 of them bidentate ligands. Okay. You're not allowed to write EN in the exam, so let's do CH2, NH2, CH2, NH2. I imagine it's probably going to call it NH2, CH2, CH2, NH2. That's perfectly fine, and you're going to get 2 of them. The neutral, so it's still going to be 2 plus. 4 ammonias. 4 ammonias are going to get kicked out, and 2 of these are going to go in. CH2, NH2, CH2, NH2. How's it written? It has done H2, H2N, CH2, CH2, H2N. Whatever. That's fine. Suggest why the enthalpy change is approximately 0, because the strength of the bonds that you break are about the same strength as the bonds that you form. You're going to break 4 copper nitrogen bonds and you're going to make 4 copper nitrogen bonds. Delta H is approximately 0. Explain why the reaction occurs despite, alright, entropy. 3 things become 5 when 3 become 5. I need some love like I never needed. Right, because 3 species become 5 species, so entropy increases. So entropy increases. I'm just going to write delta G equals delta H minus T delta S. So if that is approximately 0 and that is positive, delta G will be negative. What forms in a solution of sodium carbonate is added to a solution of gallium-3 nitrate? What? Gallium? But we only did Cu-Fe-Fe-Al. Gallium-3 nitrate solution will be this. And you have to think, well, I've done copper, iron 2, iron 3, and aluminium. Copper, iron 2, iron 3, and aluminium 3. I haven't done gallium 3, but it's a 3 plus ion, so I imagine it's going to act like the other 3 plus ions that we've done with carbonate. So I expect a fizz. So it's either this or this, because it's carbon dioxide. And I reckon I'm going to get a white precipitate of gallium hydroxide. That caused such a fuss in the real exam. It caused such a fuss. Because people are like, I didn't do gallium. Oh, lateral thinking. What's the final species produced when an excess of aqueous ammonia is added to aluminium chloride? Look, they call it aluminium chloride in the multi-choice. A solution of aluminium chloride is AlH2O 6 times 3 plus. I wonder how many of you are sitting at home trying to work out, what's aluminium chloride got to do with it? Don't know why you're talking like you're from Manchester. Alright, but it's not. A solution of, or aqueous aluminium chloride is this. Yes, there are 3 Cl- ions, so what? Right, aqueous ammonia, you're going to make the white precipitate. Look, where is it? Ammonia. It's there. It's the last one. It's going to savour this. Right, which compound gives a colourless solution when an excess of dilute aqueous ammonia is added? Right, well that does not, because that gives you a white precipitate. It's not you. Copper chloride, make that into a solution, or add a solution of like loads of water and ammonia to that, you get a deep blue solution. It's not you. Silver chloride, this is a white precipitate. You have silver ions. You make a white precipitate of this, a cream precipitate of this, and a yellow precipitate of this, and the follow-up is to add dilute aqueous ammonia, and this one dissolves, and this one dissolves only in conch, and this one doesn't dissolve, so you get a colourless solution. The answer is B. When you add ammonia solution to magnesium chloride, don't know, but that's the answer. So there you go. I don't know what that forms. I'm missing something there. What that form? I don't know where that's come up. Oh. Trying to do something here, hang on. That, same, 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 different, different, different.